been there, done that, been there, done that. And I kind of paused here because this is a concept, it's, how do I say, it's kind of an important thing in astronomy. The whole idea that if you look, it's kind of like I've been saying, if you look at something that's 4 light years away, okay, you're looking at it as it was 4 years ago. If you look at the Andromeda Galaxy 2.5 billion light years away, it takes light 2.5 billion years to get here. So you're looking at it was like 2.5 billion years ago. Does that make sense? You're looking at the baby picture, perhaps. Okay? So at some point, though, and we'll talk more about what all the evidence points to, the best theory right now is that the universe basically, and there is some play in the details at the very beginnings of our universe. The whole Big Bang is kind of the very initials being revisited. But they really think that all evidence suggests that our universe, and think about our universe in terms of like this, the space that we walk around on, okay, the matter that we walk on, and the time that we experience. Okay, like Einstein says actually the space that you walk in and the time, they are connected into this fabric of space and time. It's just beautiful. And actually there's evidence to support that, the fabric of space-time. All of that matter and space and time was this big, okay, it was small. And actually in this chapter we're going to see that there's evidence that we know that that our universe is still getting larger. Not only that, but our universe is getting larger at an ever-increasing rate. So that's actually, if you've heard it, it's accelerating. It is accelerating, okay? Because actually, when I go like this, we can see galaxies moving away. So, does that sound like you had a question?
That fast.
That fast, yeah. We'll talk more about that in Unit 4. But my point is going to be, if you go like that, think about it like that, well then there was a time, and actually we can kind of go take the clock backwards based upon this expansion, this accelerated expansion. We can go backwards, and one of the ways to know when that event happened was to go backwards, and it's about 13.6 billion years ago. 13, 14 billion years ago was when that happened. So here's the deal. If we try to look at something that is 15 billion light years away, well, our universe hasn't been around that long. So we kind of bump up with is what we call the cosmological horizon, the distance at which light cannot have, our universe hasn't been in existence long enough for light to travel that far. The cosmological horizon. And it coincides in light years with the age of the universe. That makes sense? Okay, so that's what this slide is. Okay, so with all of that explanation. So here you're looking at, this could be the Whitty Observatory. This is a dome over here in the lower left-hand corner, just a dome. You see actually there's a telescope in there, and that telescope is hard at work gathering light from those galaxies. So this is all to say that the closest galaxy, which is 7 billion light years away, is the oldest galaxy that it sees. When it looks at kind of this, and we see how this galaxy looks kind of blobby, the one that's like 12 billion, so 7 billion, 12 billion light years away. Actually, the galaxies that formed slightly early on, after the universe unfolded, these galaxies, baby galaxies, they look kind of disturbed, kind of like misshapen. Okay, they do. Okay, but here you see that actually when this telescope tries to look at a distance that's farther than the universe has been around, it bumps up against a brick wall. And that's about 14 billion light years away. It's our cosmological horizon. There's nothing coming from there. I say there's nothing, but this is exciting. This is one of the evidences of what they call the Big Bang, or our universe unfolding at a single point, is that as we look here, how do I say? As we look here, our cosmological horizon, Actually, there is something there, and it's kind of what they call the leftovers from the Big Bang. It's kind of these long microwave background radiation that you've maybe heard them talk about. Maybe not. That's cosmological horizon. Yes. So that's kind of that. Okay. Now to something a little lighter. I don't know if you caught it, but actually the Andromeda Galaxy that's so pretty, we can call it the Andromeda Galaxy, but that's a little bit wordy. The Andromeda Galaxy is also called M31. So if you're out at the observatory or something like that, okay, you'll hear them say, well, what's in the telescope? M31. Well, you know what's in the telescope is the Andromeda Galaxy. So there are different catalogs for talking about galaxies and cool things in the sky. M stands for a Messier object, and I think it's kind of funny that back in the 1700s, Messier was a scientist who was looking for comets. We'll talk about comets too. But right off the bat, you know that comets kind of come and go, and they do. Not in the same night. They're not like a meteor shower. Comets don't do that in one night. But over the course of several nights, comets will look like they change their position against the background stars. And so he was annoyed at these things that weren't comets. So he had his undergrad students basically catalog them. And they came up with 110 objects that were not comets. This is his not comet list. And these are things that we can find in our telescopes and we love. So 110 Messier objects. And so each one of these boxes is a different Messier object. So you probably kind of see the galaxies, okay, oops. That would do. The galaxy, 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 etc. You kind of see spiral arms, okay. The other thing he found quite pesky, and I'll circle a few of them, these things that I'm circling are actually globular clusters. I love globular clusters, okay. They're fun to look at. Globular clusters are clusters of stars in our galaxy. Okay, they're like somebody had a ice cream scoop and a bucket of stars, and they did this, and they put it up there. It held its shape. Okay. Then there are some open clusters. They're pretty too. Let's see if I can open cluster of these right here. I don't know if that's open or not. They're also a cluster of stars, but they're not all balled together. There's more space. Then the other thing, you see this pretty green, pretty red. Okay, those actually are a type of nebula. They're fuzzy things in the sky that Messier found annoying. And nebula are left oftentimes from stars. I guess most nebula that we see kind of glowing are from stars kind of sloughing off their material, or stars blowing up and kind of leaving what we call a supernova remnant. Okay, so those are Messier objects. All right. So, the scale of our solar system. So your textbook talks a bit about the voyage model. And if you're like me, I kept seeing the word voyage model of kind of putting things in perspective, where the sun is and where the planets are. And I've only been to Washington, D.C. a couple of times, and it was kind of like a zoo to me, Washington, D.C. But if you go to Washington, D.C., I think they have this voyage model there, where you can start here, and they actually, you can look online and see what the voyage model is, and they show you kind of how close, for instance, here's the sun, and you guys know there are 8 planets in our solar system, okay? It goes Mercury, Venus, Earth, Mars, so these are these guys here, Jupiter, Saturn, Uranus, Neptune, and Pluto. Now you can already kind of get a sense for, dang, right? These 4 are really clustered right here. Here's the sun, and after the sun, we have these 4 planets. These are the terrestrial planets. I'll put T for terrestrial, okay? And then these planets, oh my gosh, Pluto's on here. There you go. I'll put a G for gaseous, okay? And then there's Pluto. Pluto is a DP, dwarf planet. Okay, so it's good. It kind of gives you a sense for how our solar system is organized. So the opener was kind of putting things in perspective about our sun is just one star in a galaxy called the Milky Way galaxy. And there's other galaxies, like Andromeda Galaxy, and then there are clusters and superclusters of galaxies. So ultimately, if you were to look at the number of stars in the universe, okay, this would be stars and galaxies and clusters and superclusters. Okay, the number of stars in the observable universe are comparable to the number of grains of sand on Earth's beaches. So you're like, really? That's kind of cool. Here's where I've kind of been mentioning the nearest star is Alpha Centauri, which is 4 light years away, 4.4 light years away. So you've probably heard, how many people in here have heard of Carl Sagan? Oh, good. No? How many people have heard of Neil deGrasse Tyson? Well, Neil deGrasse Tyson is a contemporary, and I think I have a few videos I show of him, just kind of clips, but Neil deGrasse Tyson is a layman's, he's excited about astronomy, and he's been on the Jon Stewart show several times, kind of corrected them about how they show their Earth spinning the wrong direction. So Neil deGrasse Tyson, I don't know what else to say about him. But Carl Sagan is an older guy. He's passed since, but he was similar to Neil deGrasse Tyson in his day. Carl Sagan would say we are all made of star stuff, and here's why. We're going to talk more about this, and it's called galactic recycling in general. But the recycling part comes from stars live their lives, then give themselves up for new stars to be born. Live their lives, give themselves up for new stars to be born. That's the recycling part. Okay? Our sun has iron in it. And we'll talk about how do you know our sun has iron in it. Okay? But our sun has iron in it. S-U-N, not S-O-N. And it got its iron from other stars making iron in their cores to give back to the sun, to become an entity, center of our solar system. Eventually, our sun is going to become a red giant, okay? It's going to expand. Then the center is going to cool off, but the expanding part is going to be a nebula. That stuff can be blown to make another star. Okay. And yes, the Earth will be a crispy critter at some point, okay? So that's galactic recycling. Okay. I don't know if you can read this. Well, it's not too bad. There's a bigger version in your textbook, but this is kind of a neat thought process. If you talk about basically taking our universe, yeah, okay, saying the universe unfolded January 1st at midnight, okay, then what does that look like now? Okay, and now has to be, what is it, January, or now has to be December 31st. Like, it's squished in a year. Okay, so you can kind of see that Earth doesn't form until September, for example. But in order for Earth to form, we know our sun needs to form, and I already told you that our sun is definitely a second, third generation star. So those stars have to live their lives, okay? And they have to be born within their galaxies. And so galaxies need to form. So it's kind of a crazy sort of deal to get the Earth to form in the first place. So the Earth does its thing September 3rd. Life comes in about September 22nd. Okay, if you're familiar with the Cambrian explosion, the rise of the dinosaurs, extinction of dinosaurs, that brings us up to December 30th. You're like, dude, really? Yes. So on the last day of the year, December 31st, we've got a busy schedule, okay? 9 p.m., early hominids, 2 minutes until midnight, modern humans, okay, 25 seconds before New Year's Eve, okay? Agriculture, 11 seconds, pyramids built, okay? You kind of get the idea. 1 second ago, we're going to talk about kind of some important people in astronomy, Kepler and Galileo. 1 second ago, they were doing their thing. So that kind of puts things in perspective. I think that's kind of neat. All right. So our Earth is definitely got the motion thing going on. So this is where I kind of giggle and I'm like, you know how like toddlers, you're like, can you not sit still for a minute? No, you can't. There's various ways that we're all moving, and of course it's kind of imperceptible. One is that the Earth is spinning on its axis. Okay, it does one of these every 24 hours. You're probably already familiar with that. Okay. One of the things we need to talk about, I'm going to emphasize in Chapter 2, is that as the Earth spins on its axis, you know it kind of treks around the sun because you know the Earth orbits the sun. But just a few things that are important about that is that the Earth orbits the sun as it's spinning on its axis of rotation, and its axis of rotation is tilted. So that's why I brought this. A lot of times I will bring this. This represents the Earth's stick that it spins on, its axis of rotation. So if I make this the sun, okay, and Burlington's that way, so that's north, right? So what happens is, and it's all about counterclockwise, so make sure I go counterclockwise. So I'm going to go this way. So as the Earth spins on its axis, it keeps its rotation, spins on its axis, it keeps its axis of rotation pointed towards that way, north, as it orbits the sun. See how it's all kind of like that? The other thing, and I'll circle it on here, is the ecliptic, the plane of the ecliptic. If I were to kind of take a piece of paper, because planes are like a piece of paper, right? I could take a piece of paper, and that piece of paper kind of identifies how the Earth scoots around the sun, the plane of the ecliptic. Okay, so that's how that works. So those are two ways we're moving, but there's more. Oh, you guys needed these, sorry. Should have put these up. My bad. So as you're doing that, can you see where something we covered earlier tonight, the average distance between the sun and the Earth is 1 AU, and that's drawn there. So you guys know what 1 AU means. The tilt is 23.5 degrees. Okay, we'll talk more about that. There's more motion. I'll go ahead and make sure I put all these up there this time. The other motion is it takes a bird's eye view of looking down at the Milky Way galaxy. It's a spiral galaxy, and all of the stars, including the sun, actually are moving around the center. It's being shown up here as clockwise, not counterclockwise, which I guess is fine. But the sun goes around the center of our galaxy every 230 million years. One of the things we know is that, honestly, if there were not this motion, it would just fall into the center. This motion is important. Otherwise, gravity kind of says, all right, well, you can be gobbled up by the supermassive black hole in the center of the Milky Way galaxy. Yes, there is a supermassive black hole in the center of our galaxy. So our sun does that, so that means all the planets got to do that too. You kind of see how fast it does that. It's this motion that actually we can understand that there's actually matter outside of our galaxy. So if this is the plane of our galaxy, okay, this region we call halo, above and below the galaxy. And because of how stuff orbits, we know there's a certain amount of mass here, a certain amount of mass here. The problem is we turn our telescopes there or what, and you know what? We don't see anything glowing. There's no reason for that mass to be there. That's part of that dark matter. Okay, dark matter. It's causing this certain motion here, dark matter. We just apply Newton's law. Somebody can, I can't, but somebody else can, to understand what sort of matter we're talking about. All right. So there's even more, though. Okay, so we have the sun orbiting the center of the Milky Way galaxy, but we have the galaxy itself moving in space. That's kind of, I'm kind of getting to the expanding universe sort of thing, okay? Now, it's oftentimes, in order to kind of explain the expanding universe, we can kind of go back to this raisin bread thing, which I've never eaten raisin bread, but I bet it's delicious. I've never heard of such thing. The way this works, though, is the raisins represent galaxies, okay? So the thing is if you put raisin bread in the oven, the bread part will get larger, and the raisins kind of move with the bread part. The bread part getting larger is kind of like the fabric of space and time kind of unfolding and getting larger. That's kind of that's the universe. That's the fabric of space and time. And the raisins are just there for the ride. The raisins, of course, represent galaxies, okay? So what they say down here is if we are on, get it, the local group, the local group of galaxies, local raisin, if we're there, we look at raisin number 1, okay, and it is moving a speed of 2 centimeters per hour. We look at a raisin that's farther from us, raisin 2. It's moving even faster. It's twice as far from us, okay, it's moving twice as fast. Raisin number 3, 3 times as far, moving 3 times as fast as raisin number 1, okay? So the farther away a galaxy is from us, the faster it's moving, okay? Later on, we're going to call that Hubble's law. The galaxies actually, we see further away the galaxy is, the faster it's scooting from us, to kind of support this expanding universe. Okay, so just to kind of summarize, in case you missed it, this is all the motion we got going on. The Earth is spinning on its axis. The Earth is orbiting the Sun. The Sun is moving around the center of our galaxy. Our galaxy is moving, okay, within our local group. I don't know if I had anything that emphasizes that, but I definitely emphasize the last one, that our universe is expanding. So kind of along with the fabric of space and time getting larger, so also go the galaxies. So there is, in case you're already thinking this, there's like documentaries on this. This whole expansion thing is kind of troubling. I heard this recently on a podcast. You know, actually, as things expand, they cool, and the fabric of space and time expanding sounds like a sci-fi movie. So actually, sometimes I've heard it described as the Great Rip. Okay, so I know that's like a Doctor Who thing. So I had lots of words there.
This is in the note.
Okay.
Right?
It's
the one that you get from the library.
Nope, it's not in the,
okay.
yet.
Or in this one either?
Nope,
Okay.
nope. She's double checking that the words that are missing from your slides, where else are they? And they're just on the slides.
Okay.
But the thing is, and depending upon how badly you want that A, remember this is all recorded, so you could go back and, if you missed something. So we're going to go ahead and do a few slides into Chapter 2. I'll try not to be as verbose, but we got to keep an eye on time. Do not miss International Space Station. It's looking kind of lighter out there than I thought, though. So
You can. I can follow. You're on Twitter. I hit follow.
what's that? Hit follow?
I did.
Oh, yay! Got a follower. Okay. All right. All right. So at least just a few slides into this. Maybe.
Why does it do that way?
Oh, why does you see the circles like that?
Yeah.
Yeah. Like if you were to take a camera, I played around with doing this, like a camera where you can open up the shutter. Yeah, those are called star trails, and They're just kind of showing the star's light drag around. And just kind of like the, let's see, this is north, right? No, this is north, okay. So this is east and this is west, okay. The sun looks like it rises in the east and sets in the west, okay. So stars also look like they rise in the east and set in the west. The thing is, if you go closer to the star Polaris, okay, the thing is if you go up the horizon near the star, the North Star, that's actually kind of the bullseye thing. You're actually going to see the North Star stand still, but everything else goes kind of counterclockwise around Polaris. So that's exactly what you're seeing. Star trails. What? That isn't what I told us to do. We're just like, really? What time did I say that? 20?
19.
Okay. That's what time we need to leave. All right. Okay. A bunch of words here. So I'll let you kind of find the word. But, so how many in here have like seen the Milky Way? You may have seen it and didn't know it. To see the Milky Way, you need nice dark skies. Okay. The word Milky Way, and if you have your sky chart handy, you can find the Milky Way on there. Okay. Your sky chart, kind of that gray area, is the Milky Way. Okay. So the Milky Way looks like it goes from horizon to horizon. And if you're like, well, the Milky Way, that kind of sounds like the Milky Way galaxy. Well, actually, that comes from the Milky Way galaxy. Because what you're looking at is into the Milky Way galaxy. I have a slide here to kind of show you that. So things we see in the sky. Okay, we see the sun in the sky, we see the moon in the sky, we see stars. Stars make these pretty pictures, okay, that we all know and love. But these stars are actually, they look like they're all like stuck together, but they're really at an assortment of distances from us, okay? Usually when things are at an assortment of distances from us, if you move, I'm going to try to explain what parallax is later, but if you move, then it looks like it makes a different shape in the sky. It's called parallax because they're at different distances. But because they are so far from us, as the Earth orbits the sun, as it moves, okay, since they're so far from us, we don't see what we call parallax. So the Milky Way, that's what I said, is actually, on the next slide, oh, I guess not, coming up. So a bit about those groups of stars we call constellations. They make these pictures. So sometimes, to me, you look at the pictures and you're like, really? Is that the picture? I don't see it. Sometimes I'll be like helping out at the observatory, and little kids are awesome when they come to the observatory. If you have any little kids, you should bring them to the observatory. Don't let them run around and get hurt, but they're great. They have the greatest comments. Because sometimes you'll say, well, that's called... that's called Cygnus, the swan, or something like, well, I see blah, blah, blah. And you're like, oh, it's adorable. So there are different cultures that have made different pictures in the nighttime sky. Ours generally come from Greek and Roman mythology. On this figure from your textbook, the red lines are the boundaries, okay, between the constellations. There are 88 boundaries, okay, in our nighttime sky of all the stars that you can see from any point on Earth. What's noted here, can you see the dot, dot, dot? Can you see the winter triangle? Which we can't see, thank goodness, yet. Okay, but it looks like this, the winter triangle. I think I told you that tonight when we look for the International Space Station, we're going to be kind of looking around the summer triangle, those three bright stars. Here's the winter triangle. Okay. So just kind of some other figures. These aren't from your textbook, but just to kind of highlight a few things. Tonight we are going to be potentially looking for the Big Dipper. Where is my stylus? Evil stylus. The Big Dipper is in this figure over here. And actually, the Big Dipper is what we call an asterism. Asterism. So the Big Dipper is not a full-fledged constellation. The Big Dipper is a part of a constellation called Ursa Major. Ursa Major is the constellation. The Big Dipper is the asterism. Okay. Now, the cool thing about the Big Dipper, there's a lot of cool things about the Big Dipper. One is it helps you find the North Star, okay, which can be very handy. If you found the Big Dipper, you find the North Star by looking for the bowl. So hopefully you guys see the bowl I circled. The far bowl stars, which would be, I'll pick orange here. These two right here are the far bowl stars. Do they look like they're the far compared to where the handle is? Okay. Those actually are called the pointer stars. And if you go up, they point to, it's not very bright, but they point to a star that is in the handle of what's called the Little Dipper. The Little Dipper is not as distinctive as the Big Dipper. But Polaris is the end star, the North Star, Polaris, is the end star in the handle of the Little Dipper. So we'll get some practice with that when we're out viewing. Okay. The other thing, again, back to the Big Dipper, the other thing about the Big Dipper is you can use the handle. It's not always up in the sky, but you can use the handle to point to a bright star called Arcturus. Okay. And just kind of finishing up, because we're close to time. Over here, you actually see one of the things we're going to look for here in a minute, the summer triangle. Okay. So we'll maybe start on this slide then on next Thursday night. But let's go outside, see if we can find the, that's what it's going to do. You know what I mean. International Space Station.
Yeah,